Hello everyone, today we study calculation 2. Today, let's learn the alternating series, absolute convergence and conditional convergence. These contents will be of great help to our future study. Now, please think about 3 questions. First, how to consider the convergence for alternate series. Second, how to define the absolute convergence. Third, how to define the conditional convergence. Please pay attention to the 3 keywords: alternative, absolute, and conditional. Let's learn the definition of the alternating series. Alternating series is a series of the form A1 minus A2 plus A3 minus A4, where An is greater than 0 for all integers n. Pay attention to the regulation: positive, negative, positive, negative. Alternating harmonic series is a series like 1 minus 1/2 plus 1/3 minus 1/4. There is a theorem called alternating series test. Let A1 minus A2 plus A3 minus A4 be an alternating series, where An is greater than An plus 1, which is greater than 0. If the limit of An equals 0, then the series converges. Moreover, the error made by using the sum Sn of the first n terms to approximate the sum S of the series is not more than An plus 1. Now, try to prove that if alternating series satisfying 2 conditions, Un is greater than or equal to Un plus 1, the limit of Un equals 0, then the series converges, and S is less than or equal to U1. The absolute value of Rn is less than or equal to Un plus 1. Try to analyze the limit of Sn equals S, if and only if the limit of Sn equals the limit of Sn plus 1 and equals S. Next, prove the theorem in theory. Sn equals bracket U1 minus U2 plus bracket U3 minus U4 plus bracket Un minus 1 minus Un. By the given condition 1, Un is greater than or equal to Un plus 1, we have Un minus 1 minus Un is greater than or equal to 0, and the series Sn is increasing, because Sn equals U1 minus bracket U2 minus U3 minus bracket Un minus 2 minus Un minus 1 minus Un. The series Sn is less than U1. Then the series Sn is bounded. So the limit of Sn equals S, which is less than or equal to u1. Similarly, we can prove that the limit of Sn plus 1 equals S. It is obvious that Sn plus 1 equals Sn plus Un plus 1. From condition 2, we have the limit of Un equals 0, so the limit of Un plus 1 equals 0, and the limit of Sn plus 1 equals S, so the series converges to S, and S is less than or equal to U1. Please pay attention. Rn equals positive or minus bracket Un plus 1 minus Un plus 2. The absolute value of Rn equals Un plus 1 minus Un plus 2, which is an alternating series too. It satisfies two conditions of the convergence, so the absolute value of Rn is less than or equal to Un plus 1. Next, let's look at example 1. Please select the alternating harmonic series 1 minus half plus 1 over 3 minus 1 over 4 converges. We can analyze the problem. If the alternating harmonic series satisfies the hypothesis of theorem A, then it converges in the problem. We can know that the two conditions, condition 1, 1 over n is greater than 1 over n plus 1, which means that an is greater than an plus 1, which is greater than 0. Moreover, the limit of 1 over n equals 0, so the series converges by theorem A. Next, let's look at example 2. Does this series converges or diverge? Pay attention to the form minus 1 to the power n. It is obvious that the series is an alternating series, since the square root of x over x minus 1 prime x is less than 0. When x is greater than or equal to 2, the derivative is less than 0. Then the square root of x over x minus 1 is decreasing. So Un is greater than Un plus 1, and the limit of Un equals the square root of n over n minus 1. In conclusion, the series converges. Let's learn theorem B, absolute convergence test. Please try to prove that if the summation of the absolute value of Un converges, and then the summation of Un converges. If the summation of the absolute value of Un converges, we will have Un is between the negative absolute value of Un and the positive absolute value of Un, which means that Un plus the absolute value of Un is between 0 and double the absolute value of Un, which means that Un plus the absolute value of Un over 2 is between 0 and the absolute value of un. Let Vn equals un plus the absolute value of un over 2. It is obvious that Vn is greater than or equal to 0, and Vn is less than or equal to the absolute value of un. So, the summation of Vn converges, since the summation of un equals the summation of double Vn minus the absolute value of un. So, the summation of un converges. Next, we will learn the absolute converges and conditional converges. How to deal with arbitrary term series. For example, in the summation of un may be positive, negative, or 0. Our idea is that we can try to transform arbitrary term series into positive term series. Let's look at the definition of absolute convergence. If the summation of the absolute value of un converges and the summation of un converges, then the summation of un is called converges absolutely. Then let's look at the definition of conditional convergence. If the summation of the absolute value of un diverges and the summation of un converges too, then the summation of un is called conditional. Next, we learn theorem C, absolute ratio test. Let the summation of un be a series of non-zero terms, and suppose that the limit of un plus 1 over the absolute value of un equals rho. Consider 3 cases according to different values of rho. Case 1. If rho is less than 1, the series converges absolutely. Case 2. If rho is greater than 1, the series diverges. At this time, the general term does not test to 0. Case 3. If rho equals 1, the test is inconclusive. Let's look at example 3. Please select the series converges absolutely the value of rho, namely the limit of the absolute value of un plus 1 over the absolute value of un equals 3 over n plus 1, which equals 0. When n tends to positive infinity, by the absolute ratio test, the series converges absolutely and therefore converges. Look at another example. Test for convergence or divergence of this series. It is obvious that the absolute value of cosine n factorial over n squared is less than or equal to 1 over n squared by the ordinary comparison. Next, look at example 5. Determine the convergence or divergence. If it converges, please pay attention. when we transform the term of series equals the summation of 1 over 2 to the power n, since the summation of 1 over 2 to the power n is the O-metric series. It converges to. So, the given series converges absolutely. Now, we have the summary of alternating series. There are some methods for the convergence of the positive term series if the limit of un does not equal 0. The series divides. Otherwise, if the limit of un equals 0, try to use ratio value, root value. If they lose efficacy, try the limit comparison test. Comparison test and necessary and sufficient conditions, and some basic properties. We can also find out whether the limit of Sn exists or not. Finally, please think about this question so that this series is conditionally convergent. By the alternating series test, we can get that this series converges because the summation of 1 over the square root of n is p series, with p equals 1/2, and the summation of 1 over the square root of n diverges. Then the given series is conditional convergent. Thank you for your listening. See you next time.